Right. So thank you very much. So the title has changed a little bit, but it's you can use the two titles interchangeably, as I will explain. So maybe a disclaimer for this audience and people who know my background. This is going to be at the physics level of rigor. So there will be heuristics, there will be approximations, and there will be numerics to back them up. But we don't have theorems yet. One of the reasons why is that I was not so confident with the heuristics that I would embark in a proof directly. And it turned out that Antoine Levitt, this guy, had a new DFT code that he wanted to test with numerical challenges. So it was a good occasion to also test our theorems that I was not completely sure it would be right. So this is about magnetic Thomas-Fermi theory. So I guess in this audience, you know that this community would look very different without magnetic Thomas-Fermi theory, because that's how Jan-Philipp, Jacob, and Elliot met in the first place around this topic. So thank you, magnetic Thomas-Fermi theory, for bringing this community together. And let me start with the case, not the case I'm interested in, with a more standard one, which is a magnetic Thomas-Fermi for 2D fermions. So that's not actually the first paper, even the first, if we talk about rigorous mathematics, there were works by Lieb, Solovey, and Ingvason on the 3D, and then they had adapted this to 2D. That's what I'm going to discuss, because it's slightly simpler, and it fits better what I want to say before. So the story is, Jacob was interested in applications of magnetic Thomas-Fermi to astrophysics, but then also in quantum Hall bars, actually in quantum dots, the similar physics happened, and then they did this work. So it's the opposite of Francesca's talks yesterday. It's from astrophysics to condensed matter, and not the other way around today. So what is this? So I will not write all references, because otherwise I will be out of time. So, but this is Lieb, Solovey, Ingvason 95. So you start with the bona fide Hamiltonian in a magnetic field. So it's a constant magnetic field, intensity B, and I write it in symmetric gauge. So that's the one particle part. Then you want a dense system, which to make things smooth, to make things easy, to have a dense system, you can have a trapping potential here. So here, think of a harmonic trap, and you boost it by the particle number. That's the relevant regime to have an area of order 1 and a density of order n. So that's the regime we will be discussing. And then there's pair interactions. I'm not going to be specific about the assumptions, because this is not a math talk. But originally, this is the 3D Coulomb kernel in the paper by the Hartree forefathers. And this poses a bit of difficulty, because in 2D, the 3D Coulomb kernel is quite singular. Okay, and this acts on anti-symmetric wave functions on the plane. Right? Oops, did I destroy something important? Or is it just the clock? It's just the clock? Okay, so we will see a tweet later. Okay, so in this scaling, the area, the reference area is going to be 1, and the density is going to be n. And the magnetic Thomas-Fermi regime, so there is there are different regimes for this, but the most interesting regime is when magnetic field is proportional to density. Density is n in this scale. So why is that? Because so this Landau Hamiltonian is well known. You write what it is. It's a sum n0 to infinity. It's an harmonic oscillator that commutes with another harmonic oscillator. So I guess it's, I will probably get it wrong, but the spirit is right. It's B 2n plus half, and then pi, and this is projector on this is a eigenprojector on the n Landau level. So Landau level means the energy levels of this. Each level is infinitely degenerate. And that plays a key role. Right, so since the one-body Hamiltonian is like that, what you what you will see is that this regime B proportional to n means that on average the energy per particle is of the same order as the Landau level gap. That's what this regime does. So you have, if you thinking through a little bit, the one particle energy is of the order B, which is the gap between this level, which means that in this regime, although it will be semi-classical, the discreteness of this level still plays a role. So if you want, it's semi-classical. You will have one really classical parameter and one almost classical, which is this lowest Landau level index. And it also means that the magnetic length, which is the length scale associated to some eigenstates of this guy, will be much less than 1, which is system size square root, because we are in 2D, that's the relevancy. So and in this regime, the idea is that you're going to approximate the full many problem using semi-classical measures. So, so when we think of semi-classical measures, usually we think as a function of position and momentum. But here, because we are in this regime where the Landau level gap is relevant, the good phase space is not position momentum, it's position and Landau level index. So you have I will denote these measures by M of N and R. So they go from N cross R2 to R plus, so they are measures, they are positive measures. Basically what this says is this is the density of particles that you put in the Landau level capital little n at position capital R. So I'm not going to be more precise than that, but you can localize eigenstates of this guy so that they live roughly around a position R. So we are dealing with fermions, so this guy is not only positive, you will have a semi-classical Pauli principle, so this is bounded above by 1 uniformly. There's a particle density rho of R, which is just you sum this over all n. And if you further integrate the R, you get the particle number. Good. And then, what do you replace the many-body problem with? I mean, proofs are difficult, but the approximation is transparent. You take this, you're going to imagine that this energy should roughly look like a phase space integral, except it's a phase space sum and integral, so sum over n, integral dr. And what do you put? So it's an energy which is proportional to the density of particles in Landau level n and position r. Then you put the magnetic Laplacian, you just replace by its eigenvalue. So you're going to put 2b n plus half. You add the external potential plus nv of r. And that's the one-body part. And then there is the interaction that you write in a mean field, typical mean field way, dr prime, rho of r, wr minus r prime, rho of r prime. That's where you are. It's a pity that Michele is not here to see me put the dr just after the integral. And so this is by definition is the magnetic Thomas-Fermi energy of little m. And I'm not going to get into that right now, but if you minimize that, you see, under this constraint, under the constraint that the sum over n gives you rho of r, the part here which is only little n, you can minimize at fixed r, and it gives you a function only of rho. So if you want, if you minimize in n, you are going to get a magnetic Thomas-Fermi functional. I keep the same notation only of rho, but I'm not going to write down exactly. So you just replace this part by the ground state energy of a Fermi gas in the magnetic field B, density rho, thermodynamic limit, and that gives you this continuous by parts thing, linear by parts, which just corresponds to the slopes of this, the energy, the self-energy of rho will be the Landau level slope. Okay, so that's his story. That's Lipsolova-Ingvarsson 95, and it's a theorem that if you take the ground state of that, in the limit that I described, it's well approximated by the ground state of that. And there's work also by my PhD student Denis Peris on a related topic that I'm not going to get into. And there is work also by Fournet and Madsen, who revisited this a little bit. So I'm not going to cite everybody, unfortunately. And then since I want to use slides later, I will move all the way to the other side to discuss the thing that we want to apply these ideas to today. And so for motivations, let's discuss 2D anyons. And I'm going to discuss that. What I want to introduce is what is called the magnetic gauge picture for anyons. So what are anyons supposed to be? Anyons means something in between fermions and bosons. So what I'm going to want to have is a wave function of n coordinates in the plane. So I'm not going to put all the coordinates. I just indicate two because what I want is this. That if I exchange two particles, I pick a phase factor, which is not the the usual bosonic or fermionic one. So my basic theory will be fermionic, so that's why I say I pick alpha plus 1 here when I exchange particles, but usually you put alpha, it doesn't matter. You can change alpha to alpha minus 1 if you wish. So that such exotic objects could exist is at first a speculation, but the quasi-particles or the fractional quantum Hall effect have been with quite experimental evidence. You can believe that they are going to behave like that. So for these, I would like to have just a free Hamiltonian, just a free Hamiltonian for such a wave function. So it would be my Hamiltonian for this guy. So what is my notation? Like qualitation 0 is just free kinetic energy. And then because I will want a dense system, I put a traffic potential and I boost it by n, which is a little bit artificial as regards notation, but okay. The point is, if you are a geometer, you might want to deal with such functions, which are not functions because they are not single-valued. So they are sections of a line bundle. But if you are an analyst like me, you prefer not to have to worry about multi-valued functions. So what do? You're going to say my psi n, I can write it as a product j less than k e to the I alpha, the angle of the vector xj minus xk. So it's in the plane. So this angle of a vector is a well-defined stuff, if you just set a reference. And then times the phi n, and this one is fermionic. So this one is L2 antisymmetric as before. Now, if you do that, the idea is that you don't want to think of this guy, which is a bit formal. So this also is a bit formal. This is much more complicated than it looks. And yeah, it is, right? Believe me. And then you want to discuss the physics in terms of that. So what do you do? Well, it's a change of gauge, right? It's a singular change of gauge. But who cares? You just compute formally. This is formally the same as looking at the energy of this fermionic wave function in a new Hamiltonian which depends on the parameter alpha. And hopefully I still have room here. So Hn alpha is what you get by doing the change of gauge. So I will, it will be useful to write it like that. So sum j1 to n, you have minus the momentum minus I nabla j. So let me denote it in minus I nabla xj, then plus alpha, sum over all the other particles, grad perp of w0 xj minus xk, then squared, then is a change of gauge, so the external potential does not see it. So this, and w0 is log. It's the fundamental solution of Laplacian into the, or minus log or whatever, I don't remember. Probably I want minus log. Okay. Anyway. So that's the model we would like to look at. And in the parentheses, so it's a grad perp of W0. Yes, grad perp. So sorry. So this is you take W0, you take the gradient, and you rotate it by pi over 2. But I'm going to elaborate a bit more right now. So what does this do? So look, we have an effective gauge field now. So this is the vector potential. So if you want to know what is the magnetic field that you're having here, well, the one felt by particle j, call it xj, is the curl of this guy. So it's curl grad perp w0 xj minus xk, and that's summed over all k not equal to j. And then there's the alpha in front. Now, a curl of grad perp is the same as the divergence of gradient. So it's the same as taking Laplacian of W0. W0 is the fundamental solution of the Laplacian. So here you get delta functions. So it's 2 pi alpha, so minus 2 pi, I guess. Okay, don't you worry about the minus. I can just complex conjugate my field if I want to get rid of the minus. So minus 2 pi alpha, some k not equal to j, delta function at xj minus xk. And what do you want to do with that? Well, roughly speaking, this is the empirical function, the empirical measure of my particles. So I'm going to think that this, roughly speaking, is minus 2 pi alpha rho of xj. Where rho is the density, so it's supposed to be take phi n squared and then integrate out n minus 1 variables. So it really means what is in my title, it's density-dependent gauge field. So the magnetic field that you have is proportional to the matter density. And that's where magnetic Thomas-Fermi comes into play, because if it's a dense system, you should think that this is proportional to alpha n for a dense system. And therefore, we are in the regime of applicability of this, except your magnetic field is not constant. It's even self-consistent. So it is a little bit of a twist to think that you can apply this, but I will do it anyway, hoping that in the future it can be a theorem. And an important remark is that I start with anyons for motivation. But in experiments, what people really think that they might be able to do in the future is simulate this Hamiltonian by creating the density-dependent gauge field. And it's a little bit the other way around from an experimental point of view. It's more like maybe we can have a density-dependent gauge field, and that would simulate the physics of anyons. That's the way it goes. And so let's face it, it's a little bit speculative, especially in 2D. But in 1D, there already have been experiments with density-dependent gauge fields, in particular in the Tarwell group in Barcelona. So now, I would like to say something about how does this behave. But I need approximations, especially because I want to do numerics later. So what I'm going to do is first a Hartree approximation for this. And I'm going to discuss only ground state properties of this problem. So what does Hartree approximation mean? Well, I'm going to assume that, it's kind of the folklore that you can minimize the ground state of this by look for the ground state of this in the form of Slater determinant. So I'm going to think phi n is 1 over root factorial n, but if the normalization is wrong, it doesn't matter. It's just the normalization that you should have. Det n cross n, uj of xk, or maybe uk of xj, for an orthonormal basis, an orthonormal family of orbitals uj. There are one particle orbitals, j1 to n, and these are just one particle wave functions. Now, if you do that and you insert it in the Hamiltonian, you're going to get something, and that something, I simplify it a little bit in ways that I don't want to discuss right now. What do you get? It's convenient to write this in terms of the one particle density matrix, which is the projection on the span of these n orbitals, so j1 to n. The associated density, which is just the sum, the function sum of the uj squared. And what do you get? What is the approximation? Is that you're going to have a Hartree functional of gamma. Again, I neglect some terms that are a little bit annoying. And it looks as follows. It's trace minus I nabla plus alpha A of rho that I'm going to, I guess you know what it is, but I'm going to discuss it anyway. Trace against gamma plus n integral v rho, where A of rho at x is the integral of x minus y up over x minus y squared, rho of y. So it's this grad perp of W0 convoluted with rho. Right, so this is just, if you want, the mean field vector potential that you get if you're using this and its grad perp to define the original vector potential. Okay, so there's one thing that I want to discuss because it's fun, I think, although it took me a bit of time to accept that this was perhaps the way to go, or the way to discuss this, is the link with Chern-Simons. Because very often when we hear anyons, we hear fractional quantum Hall effect, for some theoreticians, you very quickly hear also Chern-Simons very quickly thereafter. So link with Chern-Simons. What I'm going to do in the numerics, I'm going to minimize that thing. So the equation I'm going to get is gamma commuted with some mean field Hamiltonian is 0. But if I write the dynamics for this model, that I'm not going to discuss dynamics numerically, but it's useful to think in terms of the dynamics that is associated to this guy. It's I dt gamma is h gamma commuted with gamma, and h gamma is what? It starts, as you might think, alpha A of rho squared, but then you have to remember that, so you get this by differentiating this functional. So the term I wrote is what you get when you differentiate gamma, but if you differentiate the A of rho, you get another term, which is a little bit more, let's say, fun, actually. So let me record the NV, but then I have something that I don't know by heart, which looks like minus 2 alpha grad perp W0 convoluted with the current of gamma, where current of gamma is alpha. It's easier to write it with orbitals, sum 1 to n, uj bar, minus I nabla, plus alpha a of rho, uj, plus complex conjugate. So that's the bona fide current if your vector potential is A. So that's the Schrödinger equation that is associated to that. And I want to write it in a Lagrangian picture, which is, so don't blame me, it's a formalism that I don't use every day. So this is the same as saying I have a Lagrangian of psi n, where psi n, or phi n, is the original Slater determinant, which looks like that. Sum j1 to n phi n bar I. So this is the time coordinate for particle number j. And then I'm going to add something, don't make fun out of me, but I'm going to add it for first. A is 0. And it's going to be 0 at first, but I need it anyway. Phi n, that's the time component of the Lagrangian. Then I have the space one, which is just 1 to n minus I nabla j plus a. Call that, I'm going to call that A12 on phi n, then mod squared. And then there's the, okay, there's the v. Let me not write the v each time because otherwise I get out of time. So what does this mean? Here I'm thinking I have a vector potential that has 3 components, one time component and 2 space components. So A is A0, A1, 2. That's a Lagrangian. So what do you want to do? I'm saying this is equivalent to say, I'm going to do d psi bar of integral over space-time of the Lagrangian. N is 0. But that's the partial derivative in the time component. Okay, fine. The time component for a particle j. Okay. Right, and this, but if I do this, I'm not going to get what I want, but I don't want to do this subject to constraints, subject to A0 equals 0. So don't make fun of me, it will be useful, this A0 in a moment. Even though here you are subjected to A0 equal to 0, to phi n being a Slater, as previously, and to A12. So A12 is a vector. It's a vector of the space coordinates. A12 is just A of the row, as previously. Okay. So far, so good. So this is modulo mathematical rigor. This is an identity. It's the same. And maybe because I will have slides later, I will continue upstairs. Rho is the row of the phi n. It's one particle density of phi n. Okay. That's okay. Phi here is still an n. Yes. So it's later yeah, that's a little bit sloppy. It would work for n equal to 1. But okay. I mean, it's more like in spirit, right? The only point I want to make is that what I could do to connect with Chern-Simons and so that's a calculation you can make. It's what is this? It's equivalent to saying I have a Lagrangian for phi n and the vector potential A, which is just LA of phi n, so the same as before, and some Chern-Simons Lagrangian for A. So what is L Chern-Simons? Don't ask me for details. It's A wedge dA. So it's the, that's ugly. I should do it, I should have erased the proper way. Okay, it's a sum over all the three indices, anti-symmetric symbol, so you fix this to be, it's always 1 or minus 1, you fix 1 to be 1, and then when you permute the indices, you pick the signs. A sub A, dB, A sub C, or something looking like that. Anyway, if you're familiar with Chern-Simons, that's supposed to be Chern-Simons. I think there are several variants of Chern-Simons. Very often, even this one is already called Chern-Simons. But I agree. I mean, sometimes you also add some other terms. So what I'm saying is that what I get before is equivalent to doing d phi bar of space-time integral of the Chern-Simons Lagrangian, the full Lagrangian of phi n and A. It's also, you want to do this equal to 0. But also now A is a variable, so you're going to do the same, but differentiating with respect to A. If you do that, you obtain coupled equations for phi and A, but you can solve for A. Given phi, you can solve for A. And if you solve for A in a gauge that is convenient for you, you're going to get this back. So you do this plus in the equations that you get, you solve for the vector potential A. Yes. So A has three components. It's A0, A1, A2. And A, B, C, you sum over all permutations of the three components. So that's epsilon ABC. So the Levi-Civita symbol. So I guess you're much more familiar with this than I am anyway, because you studied physics and I didn't. But then, yeah, it's supposed to be, I mean, whatever it is, it's supposed to be A wedge dA. And I write it in coordinates, but it's not allowed. You know, you're not supposed to use coordinates, but I feel more comfortable with it. Okay, then I barely have time to tell you what are the expectations from magnetic Thomas-Fermi theory. Maybe what do I put that? Well, let's say I no longer need the many more Hamiltonian, because what I'm going to simulate and show you some pictures of is just the mean field stuff, because there's no way you're going to, well, at least it's much harder to try to put this on a computer than put this on a computer. So what do you expect? Yes. Yes. Right. Mm-hmm. We did it with my student Theo team that I guess you know and who is over here. We did it in the almost fermionic limit alpha to 0. And it's correct. In general, it's not done. So let me anticipate on the numerics. Why do I neglect stuff except to make my life easier? It's just I'm going to look at Hartree, and I'm going to make some calculations, and you're going to see that the difference between Hartree for free fermions and Hartree for anyons with a parameter alpha, the difference is in the 5% range, a relative difference for energies. So when I told this to Antoine, who was doing the numerics, he was already a little bit worried, because it means he has to push his numerics to, if the error is not below 1% in the numerics, you're just calculating nothing. So if I add more terms that blur the main feature, I mean, I think it's a second step, first second step, but you really have to start with that. Otherwise, you're not going to see anything recognizable in the numerics. So what do you obtain if you take magnetic Thomas-Fermi for granted? Let me be a little bit quick. So what is magnetic Thomas-Fermi theory for this? So you have a measure, as before, of Landau level index and position. It's exactly as before. It's you have m must be non-negative, must be less than 1 because we're dealing with the basic field is fermionic. And then you copy and paste. So it's integral dr sum over n. But now you have, now your magnetic field depends on where you are. So it's a B of r. And you put n plus alpha, and you put nv of r, nv of r, m of n and r, and b of r must be 2 pi alpha rho of r, where rho of r is by definition the density associated to m, so you sum the Landau level index. Right, and now if you minimize, again, I didn't explain how to do it for usual fermions, I'm not going to explain how to do it for this, but if you minimize with respect in the n variables first, you can see that this is going to look like, you can reduce to a magnetic Thomas-Fermi theory of rho only, and its integral. So for lack of time, I'm going to write it directly. It's 2 pi times a constant depending on alpha, rho squared plus nv rho. It's just an integral dr. And this quantity here, I mean, you have rho, then rho times the quantity, which is the ground state energy of free fermions in the thermodynamic limit. Density is rho, magnetic field is also rho. So it's a bit complicated because then the Landau level energy depends on rho, but also the degeneracy of the Landau level depends on rho. So, because the degeneracy of a Landau level per unit area is 1 over magnetic length squared, so it's proportional to B, magnetic field. I'm just going to write what we did. We did the calculation. It's a really easy one once you know what you want to do, but I still managed to do a mistake at first, and Douglas corrected me. C alpha turns out to be the correct thing to do, is 1 plus alpha squared, namely write it like that, 1 minus this strange notation that I'm going to define, and then again this, where alpha minus 1 is the fractional part of alpha minus 1. I mean, this guy with, so it's alpha minus 1 minus integer part of alpha minus 1. Okay. Can we have the slides now? I'm going to, can I take a few more? Yeah, I will take a few more, but, right. Okay, so far, so these are just heuristics, and we believe that there is a theorem to be proven about this. So science is for everybody, so if you want to put a PhD student on this, you are welcome to, but I would appreciate that you tell me, because I might put a PhD student myself on this, and maybe let's avoid useful, useless competition. So okay, this was the original title, blah, 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 let me go fast, happy birthday, Yakov, etc. So this is not numerics. This is not numerics. This is the exact plot of this constant there. Where I subtract one is the value for free fermions, so it's just the Thomas-Fermi constant, which is 2 pi in 2D. So you see it does something funny. When alpha is an inverse of an integer, the C alpha is exactly 1, so you don't see that you have anyons, you see it's just as good as if you had fermions. And it does this strange stuff. And for us, what is going to be difficult is that if you look, so the reference value is 1, and it goes, at alpha is 3/4, it goes barely up to 0.12 or something, so that's the variation in the 10% range. And then when you plug this in the Thomas-Fermi energy and you minimize this, you will see that with a harmonic trap, for example, you get variations in the 5% range. So you'd better do good numerics if you want to capture that. But that's what Antoine is good at. So these are numerics. So this is this Hartree functional, harmonic trap. The black curve is the theory that you can compute exactly. Once you know C alpha, you can compute exactly that guy over here. And the colored plots are the numerical results for 25 orbitals, 50 orbitals, 100 orbitals. So you will see, so 100 orbitals is already an heavy computation, right? So what you see is that the agreement is certainly not perfect. It goes better when you increase the number of orbitals, which you can see here, but it goes better so slowly that you don't really want to crank it up too much because you will need 10,000 orbitals to really reproduce the curve. What is really interesting is that you see, so let's really, it starts looking really good at only at n equal 100. You really reproduce at least the variation. So you go to 0 when alpha is an inverse of an integer, and you reproduce at least 3 of these strange lobes here. So that's ground state energy. Now we have results for densities. And now again, densities, it's even trickier because these are the theoretical plots, these black lines. So the Thomas-Fermi for usual fermions is the thick one. And the magnetic Thomas-Fermi for fermions is the dashed one. And the thick one here is magnetic Thomas-Fermi. So you see the difference is not that huge. Also, you have to remember it's a radial plot. So what we are doing is we compute the densities of the ground states and we average over rotations to make these plots. And the numerics can see that if you take only 25 orbitals, you don't see any difference between this. You cannot catch the difference between the curves. But at 100 orbitals, the green line here, I think convincingly follows the black curve, so the one it should. Also remember, it's a radial plot. So the integration measure for this is not dr, it's rdr. So it's much more significant that here you follow the curve closely than here you have a bump in the origin, because the measure at the origin is rdr. Okay, and this is a comparison at alpha equals 3/4. Why alpha equals 3/4? Because that's where you might have the most significant signal. So I'm running out of time and badly. So I just want to leave you with one message that you can discuss if you want. This is hard to see, but if you do numerics, if you do things in momentum space, so this is momentum space distribution, there is a fit to some guess that you can take from Thomas-Fermi theory, which works rather well, and which is markedly different from Thomas-Fermi theory for usual fermions. So in particular, these are plots done, this reproduces numerics done by Tim Girardot, my students, so Antoine redid them. So this is for quasi-fermionic limits, but you can compare what you would get in ordinary Thomas-Fermi versus what you get in magnetic Thomas-Fermi theory. You compare to Hartree, and you see that really the momentum distribution clearly shows a signature of the density-dependent gauge field. So if there is an observable one should look at, that's this one. And I will leave you with that you can read. And happy birthday, Jacob, one more time. Thank you.